Elaine has given talks about her quilts to the London Science Museum and to many mathematics, science, school, and quilting groups and museums. She's involved with the Bridges organization and has presented her work there. And with co-author Diane Venters, she has written 2 books, Mathematical Quilts, No Sewing Required, and More Mathematical Quilts, No Sewing Required. Elaine will have some of her quilts on display and be there for discussion at the poster session today at the round tables in the back. So we hope you will visit her there. So without further ado, please help me in welcoming Miss Elaine Ellison for her talk, Visual Strategies for Engaging Students in the Classroom.
Thank you. Thank you, Rachel, and thank you, Enrique, for inviting me to speak. Can everybody hear me? Are you able to hear? Okay. Well, quite honestly, I can't take all the credit for the interest that the quilts have inspired for teachers, because the London Science Museum actually got me started on a hands-on activity. And this is one of the patterns that they chose. Before I did a talk there in 2002, they had put up tables, and you'll see them in a minute, where they had people from the age of 4 to 104 work on this math quilt that was going up on the wall. And so by the time I got there, half the wall was already covered using this particular pattern. Some of you know it as Indiana Puzzle. Some of you know it as Snail's Trail. In any case, it's a great coordinate proof. If you are a geometry teacher, I love teaching this as for coordinate proof. But they had a little different look at things. So here we are at the London Science Museum. These really, really creative teachers that worked at the museum set up these tables, gave the patterns to the people that were participating, would drag them off of other exhibits, ask them to fill in with this as a felt with sticky on the back. And after a week, this is when I arrived, and this is what was up on the wall. If they did measuring, I'm not exactly sure, but it actually was a great introduction to irrational numbers. And so I thought to myself, if the London Science Museum can do such magic, so can I. So you are free to laugh at this slide, because this is Pythagoras, this last year at Michigan State University Grandparents University. And I dressed up as Pythagoras. My granddaughters, Sophia and Ella, dressed up as Pythagoreans, and we told the story of the Pythagoreans, how they dressed, what they ate. The students that were in this class, along with the grandparents, really enjoyed hearing about how the Pythagoreans didn't eat beans, because if they passed gas, that was meaning they were losing their souls. And so, in any case, so this was a workshop on irrational numbers. Here's one of the grandmothers that was at the workshop. We measured the sides of these different pieces. We stuck them on. I tend to use a sticky material you can find at Michael's with a foam on the front, and sparklies are always really popular. So this was an introduction to irrational numbers. This little granddaughter actually was working with some rational and irrational numbers. The interesting thing about Wheel of Theodorus was I gave, let's see if I can highlight this. He said, I guess it doesn't show up. I gave the pattern with the first 4 triangles intact, and then the participants, along with their grandparents, had to figure out where the right angle was and also how to put the next triangle on top of the previous triangle, showing some of the irrational numbers. So this was a really great place to be sharing some math quilt activities. This little boy was a Star Wars fan, and obviously he didn't use the pattern at all, but I congratulate him. The square root of 2 is there. Yay! So in the middle of the night, I woke up and I thought to myself, ooh, I forgot about the Paducah Quilt Museum. They actually had me do some work with math teachers there also. Come to the poster session I have a little gift for you when you come to see the quilts, and also ask me about what I did in Paducah. So this is the quilt I just finished about 2 months ago. I'm really proud of the piece. It is definitely from a lady that grew up in the Midwest. It is Western mathematics. What got me started on the piece was seeing an article on the Plimpton 322. And since I saw this particular tablet, they've come out, a New York Times came out with an article recently about the updating of when the Plimpton was actually discovered. I included the Greeks in the development of algebra, Diophantus and his integer solutions, Brahmagupta's area formula, most of us have taught that in geometry and accelerated geometry. And then Al-Khwarizmi's completing the square. I was very surprised to find this on the net. And when you come to see this quilt at the poster session, take a good look at Al-Khwarizmi's completing the square. It's a little bit different than how we traditionally treat completing the square. I'm really interested in all the different cultures and their mathematics. And this particular idea has 3 of what are called sangaku. I was privileged to find these in the Kono Achimen Shrine in Tokyo. The quilt says Sugaku Tanto. I am a mathematics teacher, and there's obviously lots of hands-on things you can do with the sangaku. If you haven't investigated them, enjoy the journey. I've worked a little bit on the sacred cut. Obviously, we can do lots with this particular idea. The sacred cut actually comes from this construction, but there are only 7 polygons involved in the sacred cut. If anybody here knows why, the reason why there's only 7 polygons, please let me know, because I am curious. Can't find the answer. This is the quilt that it inspired, and it actually had 3 levels. So this was pretty challenging, making 3 different levels of the sacred cut in the quilt. Primitive Pythagorean triples. We were just talking about my friend from a Bridges conference who made a paper quilt based on the Pythagorean triples. Well, it turns out that you can take the 3, 4, 5, and you can take matrices, and there's 3 different matrices to operate on the 3, 4, 5, and you can generate all the triples that are in this particular quilt. There's loads and loads, and obviously there would be more than just these triples. So here's some triples that I did on the left, and if you want to know, I am really crazy because these are 3/4 inch little tiny squares, and there is something called Seminole stripping, so you can sew them together. But here you have the 3, 4, 5, the 5, 12, 13, 7, 24, 25, 9, 40, 41, and 11, 60, 61 on the quilt on the left. When you take and flip this around and rotate the shape, you can do the same triples on Diana Venters, my co-author, on the right-hand side, and she's also included the triple with 13 and then the triple with 15. So pretty interesting how when you play with things, you get a different pattern. Lutes of Pythagoras I found in a book by Rochelle Newman, Martha Bowles years ago. The lute is the long kind of shaped object here. I've got 5 relationships, golden ratio all over the place. Fascinating piece. This mathematical harmony piece is actually celebrating the numerical relationships that we see in music. And we know the octave is a 1 to 2 relationship, but then you've got many other relationships too, ratios of the 4th, the 5th, and so on. And that's what this particular piece was celebrating. I do participate in Bridges and have for the last 10 years. This lady on the left was a Brazilian teacher that was doing some dragon fractals and folding. On the right-hand side was a lady that's an elementary teacher over in Berlin area. And she was doing some paper sculpting that reminded me a lot of John Sharp. And John Sharp has done a lot of this paper kind of sculpting, hands-on, obviously. Students loved both of these projects. Well, here we have Fibonacci sequence, and you've seen this before, where you've got the Fibonacci numbers nested in the approximate logarithmic spiral. It actually fascinated me to see this the first time. And so, of course, I had to quilt it. And wood quilters are known for how many fabrics can you collect at any one time? And the answer here is a Fibonacci number, 55. I heard a story the other day, and this is about John Jacob Bernoulli. One of the Bernoulli brothers was complaining to Descartes. Actually, they're up in heaven, and Bernoulli is saying, I can't believe the guy did this. I can't believe he did this. And Descartes says, what did the guy do? Well, Bernoulli says, hey, I wanted this approximate logarithmic spiral on my grave. My gravestone does not have an approximate logarithmic spiral. My gravestone has, at the bottom, an Archimedean spiral. So John Jacob Bernoulli, I am sorry, but the tombstone maker may not go to heaven. And there's some Latin, autem mutato resurgo, though changed, I remain unchanged. Golden rectangle. I actually like working with golden rectangle. In Lynn Gamwell's new book, Mathematics and Art, she talks about some of the myths behind golden rectangle. So it's very, very interesting. It's about page 85 or so if you get a hold of her book. How I used this was for surface area and volume relationships, especially at Thanksgiving time. Now, this is not a Thanksgiving turkey, but our turkeys and our chickens have a tremendous problem because as Americans, we are demanding larger and larger birds, so our volumes are growing much faster than the cross-sectional surface area of the legs. And you may have seen some articles in Science News over the years. I collect those articles. This bird has really, really small relationships, surface area to volume, but he is very, very important also. So this piece right here, if anybody knows anything about the origins of where this piece, this design comes from, please let me know. I know where I found the design. However, I'd like to know if anybody knows more about it. What's interesting about this pattern is that you have, going back to Plato, you have a problem that he posed, and that's basically taking two squares that are above a larger square, using the diagonal of each of the squares and making it the sides of the new square. So the above smaller squares taken together will form the new square down below using the diagonals. Actually learned this from Craig Frederickson from Purdue, and this is from his book, Dissections, Plain and Fancy. You can see at the very top of the page where Plato has actually cut the two smaller squares, pieced them together to make one larger square. So the areas add up. Here I am at a much younger age, but you can see I still wear my little jumper. And this is the only quilt I have ever taken a hammer to. Now, most quilters would not even acknowledge the fact that they've used a hammer. But I think you can probably anticipate where I use the hammer. It's in two spots. And the two spots are where you have all the seams coming together on the right and the left. You see there's white dots there? Well, you can get that fabric really pressed down if you use a hammer, and a little bit of luck with you. So this actually is in London at the Science Museum. Great hands-on activity also here, paper quilts. Basically what you have are concentric circles. You have straight lines that are parallel. Figure out the equation of the parabolas there. Same thing with these ellipse and hyperbola. Here you have two foci points there, and the ellipse and the hyperbola. Have the students figure out the equation just by looking at the pattern. It's a good problem. Archimedes, well, this was actually after one of our Bridges visits to the Walters Museum. We saw the workings of the booklet that Archimedes had worked on, called the palimpsest. And I was really inspired to create this quilt. His face, if you can see it, well, maybe his hat is easier to see first. And then his face with the eyes, the nose, and the mouth, and then his robe. I did bring this quilt with me, so come on to the poster session and take a look at it. It was actually a problem that Archimedes was trying to solve. How many different ways can you take the polygons in this piece and put them together so that they make a square? And it turns out there's over 17,000 ways you can put these polygons together. Probably the start of combinatorics. 6 trig functions, sine, cosine, tangent, cosecant, cotangent, cosecant, secant, and cotangent. Beautiful, beautiful piece. Since I'm really pretty much a visual learner, this is the way I think about our functions. Not everybody does, but it's cool to have it hanging in the classroom. The soft cube. This was a piece the German teacher made. Really cool for young people to play around with. There's probably some really great geometry problems on this particular soft cube that moves in and out. My quilt on Fibonacci numbers. This was a Fibonacci slide. I used to take a ruler and just mark it off 1, 1, 2, 3, 5 and slide it. So that's that. A Chartres Cathedral labyrinth, a Gothic cathedral. Walking this was a really unbelievable experience, and so creating the quilt made sense. Sam Verbasi is a labyrinth maker in Belgium that does 3-dimensional pieces around the country. So he's somebody to look up. He's a Bridges participant. Leonardo da Vinci, well, his Hinged dissection. I was really surprised when I first saw this in Herbert Wells' the 3rd book. These little curvilinear shapes can actually be taken, cut apart, repositioned, put together to form what we know as the clamshell. Then, the clamshell can be cut, repositioned, put together to form the rectangle. It was thought that Leonardo was trying to square the circle. We know it's not possible now. Another Leonardo da Vinci design where your areas, you have an area doubling relationship here. Leonardo's claw, come and see this piece. I think it's a really fabulous piece. If you look at the claw on the inside of the quilt, and you look at the square that's inscribed in the claw, believe it or not, the area of the square is equal to the area of the claw. I know it doesn't look like it. I had to prove it to myself. The proof is on the back of this quilt, so when you see the quilt, turn it over. Oh, and also Cosmati, the Cosmati tilers of the 12th and 13th century did not divide the circle the way I did. I tried to make it hard for myself. This circle is divided into 36 sectors. The Cosmati used 32. Based on Pascal's triangle, this person that did this design colored all the odd numbers. Also, in the mathematics teacher, about 2 months ago, Graham Rosby did something very similar. It's not a quilt, but it has those little circular pieces in it. I thought that was very, very interesting. Another piece based on Pascal's triangle. Some tessellations. Quite honestly, I didn't do very much with tessellations in the classroom, but I do find them interesting. And this is the only quilt I think I have on it. Mascheroni was working for Napoleon, and he was very much interested in locus and locating points, especially in warfare strategies. The Graeco-Latin squares basically has no repeat in any row or any column. So you've got 100 unique cells here. And when I showed this quilt up in Madison, Wisconsin, one of the professors popped up, oh my gosh, this is the way we test fertilizers. Okay, so there's a good application. 100 unique cells, A comma B. You got it. Koch curve, oh, y'all know it. so fun. You'll see it in a minute too in another quilt. Sierpiński's triangle, loads of hands-on activities here, just loads. Snail's trail, this is what the museum picked to do. This is Diana's quilt, my co-author's quilt, but that's basically that pattern. I wanted to try some globes, and so the University of Minnesota had a really cool project where they divided this Earth sphere up into triangle globes of 20 and 121 triangles, and I was interested to see if that would actually make a quilt. Ask me about what happened to the 121 triangle globe when you come to the poster session. George Hart and Elisabeth Heathfield are really tremendous teachers. If you give George Hart a little strip of plastic with something that'll lock on it, he'll make whatever it is. And so I've gotten a lot of inspiration from him over the years. Anyway, this was a project that he and Elisabeth put together. Making Math Visible is here at their website, and you can see how much fun that the students had. Clifford Torus, well, what I like to do with this particular piece was get on Thomas Banshoff's homepage and then rotate the torus in space. It's incredible to see it flip. This was a map coloring activity. I just got a hyperbolic plane and just colored. But you can see the stereographic projection that it comes from on the right-hand side. And if you haven't done Magic Cylinder, it might be interesting for your students, all different levels. I was at a talk by Douglas Hofstadter years ago. His work was with orthic triangles, a tremendously talented mathematician. And this was in the Mathematical Monthly, MAA, publication in 2010. I really enjoyed the diagram, and now you can see the quilt. And this quilt is running around someplace in the United States. I have no idea where it is, so if you see it, let me know. It has to do with the 5 means. It's a nice piece, really cool piece. This has to do with cancer research and Jay Kapraff. This has to do with the Spidrons. If you teach geometry, you gotta do some Spidrons. These 30, 60, 90 triangles that are in the Spidrons are unbelievable, just so much fun. Buckyballs and Bubbles I have here, based on Sir Harry Kroto and Dr. Sweeney's work. And actually, here's some nice detail. When you see the quilt, you'll see that it has a lot of thread painting, and we actually thread paint with a needle. This takes hours. Magnetite and hematite, great example. This happens to be a dissection. In the lower left-hand corner is an ellipse. However, I now remember where I saw this. If you take the ellipse and you cut it, you can actually flip it and get a heart. Or if you take the heart and flip it, you can get an ellipse. Again, along the lines of the dissections. Tiled torus, if you would glue the right-hand side of the piece to the left-hand side, form a cylinder. If you would glue the top and the bottom together, you would get a torus. It was actually a coloring experiment and a morphing experiment for me. Again, a coloring and morphing experiment. Behold buttons. You may not be familiar with Andrei Kolmogorov, but when he was only 5 years old, he asked his parents, how many different ways can you sew a button on, a four-hole button on a shirt? And there's the answer. This particular quilt has been used from my twins that were 3 years old at one time up to, well, college level material. You have your combination formula. Andrei Kolmogorov. Movie Frozen inspired me to create frozen fractals. Look in the 4 corners. Well, the colors were amazing. Turquoises and purples. Anyway, frozen fractals. And Greek cross to square dissection. Here we are overlaying 2 grids. This is a piece that Reza Sarhengi, who was our leader in bridges, he's passed away now, but wrote a beautiful paper on this Greek cross to square dissection. And you can find these things on the internet too. Beautiful. Okay, there's the piece that's common. My Droste, well, it comes from the chocolate company over in the Netherlands. You can see the maiden holding a box of chocolate with the maidens, holding a maiden with a box of chocolate, holding the maidens with a box of chocolate. You can find interesting programs on the internet. I just put, well, you can tell I live in Florida because of our flowers. And this is actually the back of the Droste cocoa can. Thank you very much. Appreciate your attention.
Thank you so much, Elaine, for sharing those beautiful, beautiful pictures. And please, please visit the poster session this afternoon. Elaine has brought how many of them with you?
Oh, 6.
6 quilts with her. So she will be there if you have questions or want to discuss these with her. And we hope to see you there. So the sessions for this afternoon start soon. Please enjoy, ask questions if you get lost, and enjoy the rest of the day. We'll see you back all here together for hopefully breakfast in the morning. And for those going to the Clara tonight, if you've signed up to take part in the appetizers and games there, you just need to meet at the Clara. It's just about a block away at 5:45. Jerry Woodward will be there with a list of who's coming, and he'll just check you off, okay? So have a great day. Thanks, everyone. Thanks again, Elaine.